So there's a couple of things I've left behind and a couple of sample applications that connect to multiphysics questions that I was hoping to touch upon. So there's going to be a little bit of everything, a little bit of numerics first, and I mentioned that this morning. We're going to talk briefly about an alternative solution to the question of conservation. So we said that the volume of fluid method is a method that is pretty complex to implement, but it gives us good accuracy and has the benefit of being conservative, at least if it is implemented right. In contrast, the level set is a pretty simple methodology to implement, but and it can be pretty accurate too, but it lacks any conservation principle. So we'll propose a modification to the level set method that we'll discuss for a little while. So that's going to be the conservative level set method. This is from the work of Olsson and Kreis. Kreis being an applied mathematician in Sweden who was advising Olsson during her PhD. This method is a simple fix to the conservation issue. So the starting point will be for us to introduce a conservative level set function that we'll call psi, like we were calling our volume of fluid function. And it will differ from our classical distance level set function that we've called phi, and that we'll stick to calling phi. For any level set that we're looking at, the correct equation for that function is going to be the following. If the flow is divergence free, we can recast that in conservative form. And so that means it is easy for us to conserve our level set function if the flow is divergence free. The issue is that conserving a distance level set function is a meaningless feature to have. The distance is not a physically relevant quantity, and its conservation has nothing to do with the conservation of the volume enclosed by the phi is equal to 0 as a surface. So that's the situation we're going to resolve quickly by proposing a specific choice for our conservative level set function. And that choice will be simply the following. Our level set function will be written as 1/2 of hyperbolic tangent of the distance level set over 2 times epsilon plus 1. And we'll see why this is the first key ingredient to solving our problem. So what does it look like? Well, if I plot in 1D, if I put an interface right here, so this is my x gamma. My distance level set, we know what it is. My distance level set phi looks like this. So this is my phi. With our definition here, what we're proposing is a level set that looks like this. Between 0 and 1, this is our psi value, with our interface located at 0.5. Okay? Hyperbolic tangent profile. Well, what this looks like is a Heaviside function that's been smeared out a bit. So this looks a lot like our volume fraction field, except that we just smooth it out enough to make it usable as a level set. Okay? Let's look at, so one little detail here. There's one parameter in this, which is epsilon. Right? The effective thickness of my interface is controlled by epsilon. So now, because this function looks a lot like a volume fraction, conserving it is a much more meaningful concept. If I conserve this function, then I'll conserve something that's not the volume fraction, but that's very close. And in the limit where epsilon goes to 0, conserving this function means conserving the volume fraction. So let me write it like this. The limit as epsilon goes to 0 of the integral over my computational region of my conservative level set function is equal to the integral over a space of the Heaviside of my distance level set function times dx. On the right, I have the volume of liquid, the volume contained by the volume enclosed by my zero distance level set isosurface. On the left, I have the integral of my conservative level set. If my epsilon is small enough, one will be a good approximation of the other. Epsilon, like I said, sets the thickness of the psi function. And for this method, it only makes sense to transport psi conservatively. Okay, so this is half of the recipe. Because this is still a level set method, this thing, the fact is that numerical errors will lead to diffusion of that profile. That profile will not maintain its nice epsilon thickness. It will become smeared out, or maybe in stagnation flows, it could exhibit larger gradients. So I will still need to reinitialize that. So in the same way that we had to do a distance reinitialization for phi, I'll have to do a conservative reinitialization for my psi variable. The good idea of Olson and Kreis was to observe that you can easily write a convection diffusion equation that resets this profile at low cost. So psi needs to be reinitialized regularly with, and so the same way as before, we're going to solve in pseudo-time reinitialization equation. So I'll use a tau time here. But it's not going to be a Hamilton-Jacobi equation anymore. Those are tough to deal with. It's going to be a convection diffusion problem that looks like this. Divergence of psi times 1 minus psi times the normal vector is equal to the divergence of epsilon times the gradient of psi dotted with the normal vector times the normal vector. Where is that coming from? Well, this right here, well, first of all, let's do some high-level math. High level as in from far away. Look at this. At steady state, this is 0. I get rid of my divergence operator. What I have is an equality between the normal variation of psi times 1 minus psi and normal derivative of psi. What does that mean? That means that my variation of psi is Psi times 1 minus psi over epsilon. This is the equation that controls hyperbolic tangents. This relation between the derivative and the function itself, this will give me back a hyperbolic tangent. So this indeed will converge to a solution that looks like a hyperbolic tangent. This works as a compression term. This flows in the normal. I forgot one thing. I should define the normal. So with the normal vector being equal to the gradient of psi, level set style. No surprise, gradient of psi over the magnitude of the gradient of psi. This term is a compression term. Why is that? Because wherever my psi is not 0, no 1, it will move mass up the normal vector. So it will take my profile, my green profile above here. It will take this profile, and it will force mass to move up. So it will force my psi value to concentrate up. It will steepen the gradients. So this will act as a compression of my profile. The other term will act as a diffusion of my profile. So that other term here provides normal diffusion. Normal diffusion meaning this will try to reduce the gradient. This term will act to smear this profile and thicken it. This term will act to steepen that profile and reduce the epsilon. When those two are balanced, I reach steady state. My profile is epsilon thickness. This is a simple equation. It now looks like a nonlinear convection with a diffusion term. That's a lot cheaper to solve. It converges to the hyperbolic tangent profile. And you'll notice as well that this equation is a conservative equation. It's written as a divergence of fluxes. So if I solve my conservative transport followed by this conservative reinitialization, I will conserve my psi variable. Conserving my psi variable is close to conserving the volume enclosed by my isosurface. This is a conservative equation 2. All right, so this is the approach of Olson and Christ. There is one major problem with it. This major problem, I'll sketch it. Imagine my profile looks, my level set profile looks like this. Right? That's what we expect, a hyperbolic tangent profile. If for what reason any type of dispersion error shows up, this profile will actually become this. Okay? Overshoots, undershoots, some oscillations, it could be minor, it could be a few percent of the size of the profile. So oscillations may develop. What happens if oscillations develop? Well, in a perfect situation, my normal vector, in this case, would systematically be pointing from left to right. Right? It's supposed to be the gradient of psi divided by the magnitude of the gradient of psi. My normal vector here needs to point towards the regions of higher psi. But as soon as I have an oscillation, my normal vector will flip direction. Locally here, my normal vector will go the other way. If the normal vector goes the other way, my reinitialization equation that tries to steepen or diffuse the profile to maintain the thickness of the profile, instead of working on my actual profile, it will start working on those tiny micro profiles that have developed behind. And suddenly, I'll be maintaining and reinforcing those oscillations. The method becomes completely unstable, everything breaks. So here the problem is normal vectors will flip direction, and as a consequence the reinit equation becomes unstable because it will try to reinforce and maintain profiles that are not real profiles, that are just local small oscillations. So the conclusion is that the only way that Olsen and Kreis were able to use that method was by giving up all accuracy. The only way for them to make this work was to go to, strictly speaking, non-oscillatory scheme, perfectly TVD schemes, total variation diminishing schemes. That meant they were effectively first order accurate. And that worked fine. The method worked fine, but the accuracy was very poor. So Olsen and Kreis avoid this with low order TVD, by which I mean non-oscillatory schemes. So I played with the scheme at the end of my PhD thesis, and I realized that the only problem was the unhealthy coupling between oscillations and the normal orientation, and that, it turns out, is pretty easy to fix. If we want to fix this, if we can fix this, we can completely go back to high order transport schemes. And so to do that, I proposed what I called, and this was kind of bold, but the accurate conservative level set. Why accurate? Because instead of using low order schemes, conservative level set method, or ACLS. Instead, so the reference here is Desjardins, Moureau, Pitch, JCP 2008. And here the idea was to say, well, let's fix this unhealthy coupling. Where does it come from? This unhealthy coupling between normals and oscillations comes from our definition of the normal vector right here. If this normal vector was not directly computed from psi, we could solve this problem easily and increase the accuracy. So the idea was to say, was to use the following scheme. Invert psi, which is right now equal as a, given as a function of a distance level set, to find the corresponding distance level set. So what I do is I go back to the relation that's boxed here, and I say, well, I can invert that. If you give me the hyperbolic tangent function, I can give you a distance back. So you first invert that. That gives you a distance function. That distance function is not good. If your initial field oscillates, this distance function is going to be bad. But you can reinitialize the distance function. So once you have this distance, you can reinitialize this phi distance. And what I used, not that it's important, but I used the fast marching method. That gave me a good-looking distance field that comes directly from my conservative level set field. Now I can compute the gradient from that and build a normal vector. So I'll get my normal vector from the gradient of that distance that's been cleaned up. Because I've cleaned up my distance, it doesn't exhibit any oscillations. It's all readily usable. My normal vector will be clean. What I can do then is just throw away my distance. Yes, I've reinitialized my distance, but I only need it to get a normal orientation. I can throw away this entire thing. So compute n and throw away this phi function. I'm not going to have to suffer from the reinitialization, the inaccuracy from the reinitialization, and get rid of this. And the fourth step is to, however, reinitialize my psi conservative level set. But this time, I'm going to be using a normal vector that is non-oscillatory, that will not oscillate in any way. That means that now I can use any type of high-order schemes to solve my transport problem, even if I develop oscillations. And so we ended up using fifth-order transport, fifth-order accurate, slightly oscillatory transport, thereby greatly increasing the accuracy of the overall thing. So can use high-order schemes robustly. So this is a bit more complicated than the standard level set, because you effectively have to do two reinitializations, one of the distance, one of the conservative level set, one of the hyperbolic tangent profile. So there's one extra equation to work with. That equation is not expensive to solve, so it's not a lot of extra work. So the method is not particularly expensive. The complexity is on par with that of a standard level set, but now this method is going to be nearly conservative. Why nearly? Because again, there's a profile thickness that will tell us how truly conservative we are. Any questions on this? I want to show you quickly, I'll show you like 3 or 4 slides that compare the performance of this with the VOF method that we've looked at yesterday. So I'll unplug myself from here. At least I'll try. So let me show you quickly. This is taken from a short APS DFD meeting set of slides where we were presenting the performance of this method. So I'm comparing this UVOF, U standing for unsplit. This is the method we've been talking about so far. It's a version of what I showed this morning as well. And this is this accurate conservative level set. The question we asked is now both of those methods, one is pretty complicated. I guess I'm not going fast enough. One is pretty complicated to work with me. Thank you. So one is pretty complicated to implement. The complexity, the computational complexity here is high. This one is low. This one you implement in a couple of hours. Back to our notched circle problem. One rotation, I think this is one rotation. Yes, one rotation on 3 successive meshes, 50 squared. So this is what we've been running so far. The UVOF scheme, wait for me. I'm going too fast. The UVOF scheme that I used is a bit better than the one that we talked about together, but it's pretty similar. So the performance corresponds more or less to what we saw. Even if you go to a coarser mesh, well, you start seeing more deformation, but things are pretty good. ACLS is very much comparable. Yes, it doesn't quite preserve this notch as well, but there's very little value in really preserving this notch. It's just one error like any other. I can show you, so what's going to happen is this VOF scheme is going to be exactly conservative. If I compute, well, here I said volume, it's really the area enclosed by this notched circle. The transport error for the total volume enclosed is 0, right? Essentially machine accuracy, almost. We expect this. The method should be conservative. ACLS, it's not going to be 0. We have a profile thickness. We don't conserve the quantity that is exactly the volume under the isosurface. We conserve something that's close. But the resulting conservation error is small, in the order of 10 to the minus 4, 5, and then it goes to essentially machine zero pretty quickly. This is the error made in the shape at the end of the rotation as a function of the time per time step. So this is a true assessment of the performance of the schemes. This is error versus cost. How much does it cost to run the time step versus what is the resulting error from the method. So this shows you that in fact ACLS ends up being a more effective method. You get more bang from for your buck. You end up systematically having a lower error at a given cost, or vice versa. If you want to reach a certain level of error, the cost is less with ACLS.
That shape error is like a deviation from the...
Yes, this is the deviation, exactly. This is the integral of the mismatch between the initial condition and the final rotated solution in an integral sense. So we don't cancel out corners rounded from one end to the other, and we just integrate the complete mismatch. We can play with the deformation problem that we looked at already. Again, the performance is pretty similar, but here we have to admit that ACLS, because the profile has a little bit of a thickness to it, it ends up breaking the ligaments and undergoing deformation sooner than VOF. VOF is truly able to resolve something on the scale dx. It is not really the case with ACLS, which has a somewhat larger thickness. Let me skip this because it says the same thing. Again, if you look at cost, what we find is, not surprisingly, solving a level set problem like we noticed yesterday, it is pretty cheap compared to solving a VOF problem. Yes? Oh, I did not say that. Yeah, that's a very good question. I use for epsilon the value of dx over 2. Effectively, that leads to a profile that sits on approximately 3 cells. So that means that the effective resolution, the effective thickness is, more than dx. It's a coefficient times dx. Yeah, that's a good question. So the profile thickness is set by an epsilon that is set to delta x over 2, which leads to a profile that goes from 0 to 1 over approximately 3 cells. To contrast again with SPLIC, which sharply goes at from 0 to 1 at the location of the interface. Wait for me. So what was I saying here? I do not remember. Let me go back. Yeah, so the cost is almost an order higher. VOF is an expensive scheme in comparison to a level set. So the VOF scheme is about 5 times more expensive. It has a better capability of maintaining ligaments on the smaller scale. But overall, in terms of performance, accuracy versus cost, ACLS seems to be the better deal. And then just for the sake of a more concrete comparison, we're going to look at one jet at Reynolds number 5,000. It's a round liquid jet with a Weber number of 10,000 with both methods. So the jet goes from left to right, undergoes breakup. The flow field is turbulent. We get this mushroom shape that we were looking at in our little 2D toy problem. But now the flow is turbulent. This thing breaks a number of ways. You can see that there's very strong similarities between the flow. The early part, things are essentially nearly impossible to distinguish. The same features are visible, the same corrugations. Now the timing is right. Later on, you can see that this mushroom cap shape is forming a sheet. This sheet is better maintained, even though it does break in various places. It is better maintained by VOF than it is by ACLS, where you see tearing in this sheet at multiple places. Again, the effective resolution is higher with ACLS. And finally, when you go further downstream and you look at some of the very elongated ligaments that are formed with VOF, you can see that you don't really see the equivalent structures, even though there's fairly similar collection of droplets that used to be ligaments. And again, that indicates that breakup happens sooner because effective resolution is less. Overall, mass conservation error for the entire problem is almost the same. It turns out that even VOF being exactly conservative, if our flow field is not discretely conservative, that means if we are not exactly to machine precision solenoidal, we will still have some level of mass loss even with a VOF method. And so ultimately, both methods lose approximately on the order of a couple of % of their mass. And so the fact that ACLS is not exactly mass conserving ends up being irrelevant to this. Both methods perform equally well. Again, in terms of cost for this problem, you can see that UVOF is about twice the cost of ACLS. The other interesting thing, so here I'm plotting time, accumulated time as a function of non-dimensional time. Another interesting thing, this is a linearly increasing time as a function of simulation time. Why? Because the amount of work I do here is independent of the amount of interface. I'm solving PDEs. In the other case, with VOF, the amount of cutting that I do to figure out my transport, that's proportional to the amount of surface area. So the amount of stuff I need to cut is less initially and much more later. Therefore, you can see that this curve is incurving. So anyway, that's what I wanted to show in terms of the performance of the method. That suggests that it's not that clear that VOF is the go-to method. It is a functioning method, certainly, and it's an appropriate method. But you can conceive of alternative schemes that can be simpler and more accessible in general. Okay, so now I want to touch upon those three topics, each of them briefly. So I'll give you a high-level overview of some of those different directions that are all current research directions that start from a multi-phase problem and expand from there. Stop me with questions, by the way, right? I'm kind of rushing through, but I'm happy to stop anytime. So the first thing relates to what we talked about this morning. This morning we said, wouldn't it be nice to have the capability of performing active control on our spray? Well, one way that one could achieve this would be by electrifying your fuel injection process and using electrostatic forces to enhance or disrupt atomization. So the concept here, so we're going to talk about electro-hydrodynamic atomization. The concept would be if instead of just introducing a liquid, I introduce the charged liquid, then the charges present in the liquid should lead to repulsion within the liquid just due to the Coulomb force. And that should lead to a more rapid explosion of the jet. There's more to it than that. So you could expect an enhancement of atomization, but you need a force, an electric repulsion that would have to be applied to the nozzle itself. The nozzles tend to be very small, so the amount of energy involved here in charging up the system electrically is not high. So the energy requirement is not high. If you're capable of introducing this repulsion, then that means that your spray would open up wider and that would enhance the dispersion, which is typically a good thing. And then once you're done with the breakup, you have now charged droplets floating around. Well, a charged droplet can be controlled. You can now apply an electric field and you can make your drops turn left or right. You can remotely apply force to those drops. And so that has a lot of interesting applications, and even going down to the evaporation process. There's an interesting phenomenon called Rayleigh Breakup. Everything has to do with Rayleigh or Kelvin or Helmholtz. So the Rayleigh Breakup is the following phenomenon. If I have a droplet that's charged, the evaporation will not change the charge density or the amount of charges in the droplet. So as the droplet evaporates and shrinks, the volumetric charge in that drop will actually increase as a function of time, to the point where I have such a high charge density that the drop will simply explode due to the Coulombic repulsion. So that means that an evaporating drop will end up just extremely violently responding to the charges once it gets small enough. And that could even further accelerate the evaporation process. So if your goal is evaporation for combustion applications, it might be that charging the drops is overall, regardless of the atomization, it might be a very good idea. Now, however, doing experiments of that is difficult. We don't have a particularly good understanding of this process. And I should say, so this comes from one of those experiments. It comes from the UK, from Shrimpton at the University of Southampton. On the left, you have a kerosene jet under conditions such that we expect no breakup. Essentially, this is a Rayleigh plateau type of condition. This is your very low Weber number condition. This jet extends forever, and then it will drip with big drops at the bottom. If you charge it, that's what you get. This Coulombic repulsion is sufficient to break this thing apart. So we played with this problem over the years. Formulating it is not too complicated. This was our starting point, our single-phase, two-phase uncharged problem. Now we're going to have to account for the presence of charges within the liquid. We're going to assume we don't have to worry about charges within the gas. And from a timescale analysis, we're going to make a big assumption, which is the assumption that oh, no, I'm sorry, I didn't make this assumption here. So, yeah, we're going to be solving for charge transport within the liquid, and we're going to be solving for the self-precipitating electric field. So what is the charges present are going to generate an electric field, and the charges are going to respond to this electric field. So the Navier-Stokes equation are essentially the same as before, except for an extra stress tensor called the Maxwellian stress tensor that comes from the presence of an electric field. So that's the expression for this stress tensor, where epsilon here is the electric permittivity of the fluid, and E is the electric field. To obtain the electric field, you just take minus the gradient of the electric potential phi. This electric potential you can obtain from the solution of an electric Poisson equation. That looks like this. Divergence of epsilon grad phi is equal to minus Q. Q here is the electric charge. 0 in the gas, and in the liquid, it is going to be obtained by an equation that conserves the electric charge. We're going to write an evolution in time of the local charge concentration. The charges get advected with the fluid. They are going to move due to the electric field, and they're going to diffuse within our fluid as well. The big challenge here lies right in here. This epsilon is not the same within the liquid and within the gas. So the electric permittivity of the liquid and the gas are not the same. They're discontinuous. This is a discontinuous coefficient Poisson equation. This is as difficult a problem to solve as our pressure Poisson equation is with this 1/ρ embedded inside. The good news for us is we know how to solve this. We talked about it a couple of days ago. We have the solution process. We can make use of the same goes-through-it technique, and that's what we're doing here. So we're going to just look at one example of what you can do with a technique like that, and in theory, we can solve all this. So we're going to look at the same jet as before, a Reynolds 5000 round jet coming out of a round nozzle. The Weber number is low enough. So this is based on liquid properties, and so it is low enough that we're going to have corrugations, but we wouldn't have significant breakup on the system. This is density ratio, ratio of the electric permittivity, et cetera, et cetera. And so we're going to inject this with a charge characterized by an electroinertial number ratio of the potential for the Coulomb force to the inertia of of about 10%. So that the Coulomb force we expect it to be about 10% of the inertial forces. On the top, we have the uncharged case. The inflow is turbulent. The flow comes in turbulent. So there's corrugations developing, but there's not a lot of excitement happening right here. On the bottom, we have now the charged problem at about 0.5 Coulomb per meter cubed or something like this. So what do we see? Well, we see that indeed this jet is kind of pulled apart. And we see those corrugations that are forming here. They end up being repelled, and they are torn apart from the central part of the jet. In the process, we form sheets, and we find that those sheets, either due to lack of mesh resolution, I certainly again say every time we form a sheet, I wouldn't bet about the physical correctness of what we're doing, but we find this fishbone structure type of thing, those long ligaments that are now radially outward oriented. They all point out from the center. In terms of comparisons, it's a little tricky. we don't have a lot of quantitative data. In fact, we don't have any. We have some qualitative data. So going back, so we can find some experiments at similar Reynolds and Weber number for non-charged jets. That's not too complicated. This comes from work by Stephen Lin at AFRL. This is an X-ray radiograph of a somewhat higher Reynolds number jet, straight jet, with no charge, and you can see a corrugated surface. Things are pretty boring. There's not much happening. The charge condition matches the Shrimpton experiment I showed you before. If you scale things so that we match exactly those conditions, you can see that we have some qualitative matching in terms of the amount of spread from that jet. It's still pretty far from being quantitative. We don't have, again, any data. The interesting thing is that that fishbone structure that we see early on, and that we can't see here because of lack of the resolution in the shadow graph, it seems to still exist downstream. So it's maybe not that surprising that we would find those radial, those ligaments oriented radially outward. And from that, we can also study what happens to the charges. So you can see that this is now the charge density going up to, well, this is scaled to highlight what's happening. But you can see that the charges are also being transported within the liquid phase and end up accumulating towards the regions that are the most, so the charges are rushing out of the central core. Here we're looking at the jet head-on, and they are accumulating in those drops and ligaments that are being pushed the furthest from the central jet. Okay, so this is something we've started looking at with the hope of performing spray control, but this is still very early on. I'm not going to say any more than that on this. I don't know if there's any questions. If not, we'll just jump to the second little toy problem that I want to discuss. Yeah.
What happens to the effect of this EHD control on the kinetic energy of the jet?
I don't know. I would expect there's no major influence, but we do certainly we are increasing the mixing of this jet. It's being expanded, so I think it should experience more drag from the fluid. It should slow down. So it's a good question. We did not look at that. We didn't characterize anything from an energetic standpoint with this. But it is an interesting question. I would expect there would be an influence. Yeah. Okay, so the second topic is going to be, instead of adding more physics, we're going to be looking at the exact opposite exercise. Let's try to zoom in and simplify the physics as much as possible and simply consider the most basic process taking place in some of those problems. So we're going to remove most of the stuff that makes our life more complicated in order to try to say something concrete about the interaction between turbulence and interfaces. So our objective here, so this is kind of a small project that's been going on for a little while in my group. I have a number of slides, but they're all too detailed, but I want to take the opportunity to just show this couple of cases. We're interested in the question of how one would model the corrugations and deformations that are created at an interface that is exposed to a turbulent flow. And the way we've done that has been by looking at those very toy problems wherein we have a box of homogeneous isotropic turbulence and we're placing an interface in that. We just immerse an interface in this thing. We're not considering, so we're considering that we have the same fluid on both sides. So we're not dealing with density ratio, we're not dealing with viscosity ratio. We're treating this as a surface that experiences surface tension, nothing more. So turbulence will wrinkle that interface. The interface will interact with turbulence in a very canonical way by trying to flatten it to become flat again. And in the process of doing so, it will modify the characteristics of turbulence. So it is a two-way coupled system wherein an active interface is interacting with a turbulent flow. So like I said, so the main goal here is to characterize the length scales that develop in the turbulent flow. as well as on the interface. We can start from a flat plane, and that looks like that, or we can start from a collection of randomly distributed droplets or bubbles, and as we stir this, we get some statistically stationary state. So one thing I'll show is specifically the scales of interface deformation. So I'll show you that we can quantitatively say a few things about that. We're also interested in the question of using those data sets to extract larger dissimulation models. So the type of stuff that we're missing, what is the physics taking place at the subgrid scale if we don't resolve all the scales of the turbulence and interface interactions? So this is a triply periodic problem. We don't have gravity, we don't have a density ratio, we don't have a viscosity ratio. We're just going to vary the amount of tension on our interface. Same methodologies computationally as before. And I'll just show you essentially this slide here. Well, maybe the next one too. We're extracting two things here. One is a spectrum of wave height. So we're looking at the spectral content of the two-point correlations of the height displacement of the interface. What that means is we're looking at what are the length scales, what is the distribution of probability of finding length scales at on this interfacial displacements. Okay, so we're looking at an initially flat interface. It corrugates, the height changes. This is now fluctuating quantity. We extract a power spectrum of this in order to be able to say whether we have more corrugations on large scales, on small scales, or things of the sort. And what we find is that our volume, well, in fact, this is not what I'm plotting, I'm sorry. So the other thing we're looking at is just the spectrum of the volume of fluid fluctuations. So we take our volume of fluid field. It is a fluctuating quantity. We just ask ourselves in a standard turbulence analysis way, what is the spectrum of those turbulent fluctuations in volume fraction? And we find those curves here. They're generated at 4 different conditions. One has no surface tension. And then we have increasingly lower Weber numbers. So we start from infinite Weber number, no surface tension, and we start putting some surface tension, and then more, and then more, and the last case has the most surface tension. And what you can see is that we have a flat component of our spectrum, and then as the Weber number decreases, we also get a second slope that shows up, and where that slope shows up moves left, so towards lower wave numbers as the Weber number becomes less. So we'll add another parameter here, and that's the probability density function of finding a certain level of curvedness. What is the curvedness? It's like the curvature, except the curvature is not a practical quantity to use, because a saddle point, a region that is most definitely curved, will see both a positive and a negative curvature, so the total curvature will be 0 at the saddle point. The curvedness fixes that by looking at a sign agnostic measure of the local curvature of the interface. So the curvedness is a geometric, it's going to be the product of the principal curvatures, not the sum of the principal curvatures. Anyway, so we have some measure of the curvature, and what we find is that that curvature peaks up at a certain point. So it seems that there is a low likelihood of finding very low curvatures in our flow, a low likelihood of finding extremely high curvature in our flow, and some higher likelihood of finding some intermediate level of curvature in our flow. Those points, they all correspond to one another. This peak, this peak, this peak at those 3 Weber numbers, it corresponds to the location of that break in slope, that break in slope, and that break in slope. And that's the different Weber number. So what we're finding is that no matter what we analyze, there seems to be a pretty important length scale that shows up that controls the interaction between turbulence and interfaces. That length scale, it turns out that what we're looking at here has been studied for a while In particular, it started with Kolmogorov, who first hinted at the existence of this. This is something that Kolmogorov referred to as a critical radius. And what that is a statistical concept of a length scale at which turbulent eddies would have just the right amount of energy to interact with surface tension. So any larger eddy would be able to deform the interface because they have more energy. Any lower size eddy would have not enough energy to be able to push against the interface because the interface pushes back due to surface tension. So if you balance surface tension and the energy contained in an eddy at size L crit, what you work out is this relation. And that relation matches well with those peaks that I showed in the curvature function before. So anyway, what I showed here is that if you want to model turbulence interacting with an interface, that's a length scale that you need to worry very much about. And I should say, what is that length scale? So this, sigma here is surface tension coefficient, this is density, and this is the energy dissipation rate. That thing here will tell you, any scale larger than this, the turbulence will be able to deform your interface. Any scale below this, the turbulence will be seeing this interface as a wall, and it will not be able to interact with it. So if you're doing an LES where your mesh size doesn't reach that, it is larger than this, the story is going to be very different in terms of what needs to be modeled than if you're doing an LES where your mesh size goes below this. So that's something to consider. Okay. So I had a couple of more things, but I wanted to skip those. So I have one last topic that I want to talk about, except if there's any question on this turbulence interface interaction exercise. If not, we'll talk a bit more about this liquid-jet supersonic crossflow problem that I showed briefly this morning. So this is in relation to the discussion we had about scramjets. Scramjets can be operated with a gaseous fuel if they're already hot, but if they're just starting up, they're going to have to work based on a liquid fuel. And so in a situation like this, you need to deal with the problem of liquid fuel injection in a supersonic crossflow. The scramjet is a simple supersonic flow passage. You have little holes, you inject your fuel in that, and you hope for the best. There's not a lot of tools capable of computing this. And so we were tasked a couple of years ago by the Air Force Research Lab to develop such a tool, to port some of our tools that we've mostly, like you've seen, we've worked essentially mostly with incompressible assumptions. We've been tasked to port this to compressible flows. Our observation, or at least our understanding of the problem, led us to do the following things. First, we observed that yes, the gas phase is going to be supersonic at the entrance of the domain. When you inject your liquid, it's a low-speed liquid, you're going to form a shock. The gas phase will become subsonic, and then it will re-accelerate to supersonic conditions. Okay, but the liquid itself is very much a low-Mach flow. Locally, the liquid here, first of all, the speed of sound in the liquid is very high, and second, this liquid is injected at low speeds. So we have a flow that is characterized by a pretty high Mach in the gas, but a pretty low Mach in the liquid. So ideally, we would want to have a method that can deal with the high Mach flow characteristics without being stuck with resolving the time scales associated with the acoustics inside the liquid. And so because of that, we decided to go after a fully implicit treatment of acoustics. So in fact, we're going to use methods that are still going to be based on the pressure projection algorithm so that our acoustics are handled implicitly, and I'll show you that in a second. And then we want to have stable schemes. We want to be able to maintain robustness. All those semi-Lagrangian remapping schemes, those semi-Lagrangian flux schemes, they're extremely robust. So we're going to make use of those schemes directly for transporting all our variables. So far we were transporting only the VAF variable with this. Now we're going to transport everything. Density, momentum, total energy, volume fraction of the phases, everything will be transported with the same approach. And also thanks to those schemes, which I argued were second order accurate, we're going to be able to maintain second order accuracy. So this is a set of equations we're solving, an equation for volume of each phase. The subscript here indicates the phase. So for each phase I, I'm going to be solving for the volume. This is my volume fraction equation, written in conservative form, but now my divergence of the velocity is non-zero, so I have to account for this right-hand side. This is conservation of mass for each phase. This is conservation of total energy for each phase. And finally, this is a shared momentum equation, assuming that the phases have a continuous velocity. So this, like I said, we're going to treat this problem the same way that we've treated our VAF transport. Second order geometric scheme based on a semi-Lagrangian volume of fluid treatment. And this is going to be based on the Plick reconstruction. That means that I can deal with the liquid fraction of the cell, the gas fraction of the cell. All this is known. I can brute force this problem without any problem. By the way, one property we didn't talk about explicitly, but the scheme we put together together yesterday, it is unconditionally stable. Because it is semi-Lagrangian, it doesn't care about the time step size at which you run it. You cannot break this scheme. It's an interesting property. To contrast with the split scheme that has only that has an assumption of a CFL not going higher than 0.5. If you remap the entire cell like we've done, there's no such thing as a CFL limitation. I showed you this morning, even if our remapped cell, our Lagrangian transported cell, is completely deformed and folds over itself, we can still compute it. Of course, the accuracy decreases the higher the time step size. This is the acoustic part of the problem. We're going to recast that by formulating a pressure equation. And that pressure equation will solve implicitly in a projection step. So we'll do a velocity, energy, and density predictor, and then we'll do a pressure correction in the same way that we've done that for our fractional step method. This equation is formulated from the momentum equation. It is not a particularly complicated equation to derive. The important thing is that we're solving for Pn plus 1, and you can see that everything here involves the new pressure, Pn plus 1, Pn plus 1. That means that we're truly solving here an implicit equation for the pressure. That means all the acoustics will be handled without a time step size restriction. That equation in nature is, if you were to remove this, as well as remove this, this would be our pressure Poisson equation from the incompressible realm. This is the divergence of 1 over rho grad P is equal to the divergence of the predicted velocity. So in an incompressible setting, that takes us back to our incompressible flow solver. So that's going to be fine at low Mach. At high Mach, what happens is that this extra diagonal term will become larger compared to these, and we'll end up in a situation where the nature of this equation will be no longer elliptic. In fact, this problem is now not a Poisson equation, it's a Helmholtz equation. So it's a significantly easier equation to solve because it's not fully elliptic. Viscosity is never a problem. We'll solve it implicitly as well, but there's no real concern here. Viscosity would discretize second order accurate with no concern. The body forces are not really a problem either. We use the same gauge-free treatment in order to introduce our surface tension force. So this F here will contain also the surface tension force, which we'll discretize like we've done together a couple of days ago. So overall, the entire method is, except for the surface tension, which is handled explicitly, it is unconditionally stable. It is exactly conservative and formally second order accurate. So a couple of test cases to show you. We threw a shock at the drop in the liquid column in 2D. So now I don't know if you can really see this. Down there, those are the experiments by Igra and Takayama from 15 years ago, a little more than that. And so this is an experimental Schlieren, and we have a corresponding computational Schlieren with the little drop here in the middle. So this is a shock wave hitting a liquid column and then reflecting, and then later on the drop just breaks up. This is an experiment by Theophanous from about 10 years ago. This is now a liquid droplet, so this is a shock hitting a liquid droplet. You can see that there's some capillary waves that respond to the shock passing by, but for the most part we end up feeling the effects of the shear at the surface. This is a Weber number that corresponds to our surface shearing conditions for the drop breakup. So you can see the drop flattens and we start pulling liquid from the side. I don't know if you can really see from the simulations, but the same thing happens. The drop flattens a bit and we form ligaments on the side that are being pulled off. Yeah, I'm not sure you can really see this. This is a simpler two-phase shock problem. This is throwing a discontinuity in 1D at a liquid-gas interface. And this is just checking that we can run at pretty much any CFL. So we ran with a convective CFL of 4, for example, and you see that the results, there's multiple lines that are superimposed here. The result doesn't respond much to the increase in CFL. Ultimately, our goal was to run a liquid jet in supersonic crossflow. And so we got some experimental data from AFRL, a boundary layer profile from AFRL. We got various conditions. And we plugged all this in a little computational domain around our liquid nozzle. And we ran first very coarse simulations, and then increasingly finer simulations of the problem. So this is a coarse simulation, proof of concept. Yes, it seems that the method works. Then we refine our mesh a little bit. You can see a bending jet. The coloring, I don't know if you can really make it out, is a numerical Schlieren. What matters here is the fact that you can see this bow shock forming just upstream of this liquid jet. Go to even finer resolution. You can start to see waves forming at the surface, ligaments being pulled off from the sides. Things are becoming a bit more exciting and a little bit more rich. Ultimately, our finest resolution looks like this. We have the surface waves developing. We're pulling ligaments off the side. This conserves mass fully. You can see again our bow shock forming right in front here because this low speed obstacle that the liquid is subjected to. We've just barely started to compare this against experiments. This is our increasingly finer resolutions. We're looking at the location of the bow shock, the average location of the bow shock, as well as the penetration of the liquid jet. I don't know if you can really make it out, but the experimental penetration is given here by this gray line. And what we've seen is that refining the mesh didn't get us very close to our expected results, but as we started introducing turbulence in our liquid to match with the experimental conditions, this is our purple jet here, things are starting to follow more closely the experimental penetration of this liquid jet. So we're making some headway with this. We think we have a method that's robust and that seems to be capable of dealing with supersonic atomization type of problems. Okay, so this is those are the three extra applications that I wanted to talk to you about. So how, basically looking at how those VAR for level set methods can be used to look at increasing either more finer detail problems or increasing complexity by adding more physics to the problem. Any questions on this?
I didn't get that. You told you don't have a CFL criteria. You have the equations. So only the phase transport equation would be solved using the Plick approach.
No, that's what I'm saying. Everything is solved using the same Plick approach here. So we're using this Plick VOF type of idea to solve all of our equations. Why? Because obviously the volume fraction is discontinuous, but the density is discontinuous as well at the interface location. the total energy is discontinuous at the interface location. The momentum is continuous as well. The velocity is not, but the momentum is discontinuous as well. So we're relying on the Plick to tell us where all the variables are discontinuous. And then we use the semi-Lagrangian remapping of our cells to figure out, to do our entire transport. Because it allows us to say, well, that cell back in time was there. I know where the interface was, so I can split that old cell where it was at the old time. I can split it and look only at the gas side of it and liquid side of it. And then on the gas side, you'll interpolate gas values to figure out what comes into your flux. And the liquid side, you'll interpolate liquid values to figure out what comes into your flux. You collect all that, and that's now a new value in your cell. So this doesn't have anything to do with the CFL treatment, with the absence of a CFL. But this has to do with the fact that, yes, we are using the same scheme that we've talked about yesterday for all of our variables, for all the transport. Why is it free of any CFL condition? Because if you look at it, we never actually write a PDE, an explicit PDE type of formulation. What we say is that cell in the past was there, and the value there was that. And that value needs to be preserved upon transport. This is, those are semi-Lagrangian statements or Lagrangian statements regarding material transport. Saying, so, and those are not subject to any CFL restriction. So if I take a particle, I say the value of a quantity at the particle location is constant, it doesn't matter to me where the particle is or how I'm sampling the position of the particle. It only matters to me that this value is constant. There's no CFL associated with that. Now, when I backtrace, like what we did yesterday, if you take that cell and take it back in time, the tracing back in time, this is solving an ODE. This is subject to a CFL. But we can substep this. So as long as you can take a cell and bring it back in time, which is not a particularly complicated thing to do, the resulting scheme has no CFL limitation. So I can take that cell and move it back to the 10 cells away. The resulting scheme will be stable. Inaccurate, but stable. So that means that there's no CFL coming from this. This is solved implicitly, so there's no CFL. And this I solve implicitly, so there's no CFL either. So I end up with only CFLs coming from this, which is surface tension. Other questions? Yes. Of course. So you're interested in what? In yeah, so I'm assuming, so there's a number of assumptions here. The assumption here is essentially an electrostatic assumption. I'm assuming that I don't need to solve the full Maxwell equations. I'm treating this literally as an electrostatic problem. So I'm not going to care about the induced magnetic field. This is Ohm's law. That's all I'm doing. I'm assuming that this is reasonably represented by Ohm's law, and that's what I use to relate my potential to my electric field. So this is a standard approach with an electrostatic assumption. I should point out, the nature of this problem is interesting. When you charge a liquid, you would expect all the charges to rush to the surface if the liquid is a conducting liquid. We're interested in atomizing or enhancing the atomization of fuels. Most fuels are near perfect dielectrics. So they don't actually conduct. So you can charge them up, but the charges are not going to do much of anything. There's not going to be much motion of the charges within your liquid. That means that essentially the charges are mostly going to be controlled by that term, which is just the convective transport at the fluid velocity. So we find that, in fact, if you don't solve that equation, if you just place your charges somewhere in your flow and have them move with your fluid, you model this process in a way that's fairly similar to if you solve a full conservation of electric charge equation. Did you have any specific questions on this, or? So the big assumption here is we're staying away from Maxwell's equation. We're working with a static assumption. Okay. Other questions? I'm just remembering that I forgot one little thing. Give me 1 second and I'll show you. So I did not finish that. I forgot to finish that. And we're not going to finish that. We're essentially done. But there's one really beautiful study on atomization. I want to say one word about it. This is a study by Mamoto and Villarmo. This is a JFM 2004. And I've been talking to you about waves. And I should have mentioned that this is a really beautiful study that explains very nicely how a gas can break up a liquid if all the momentum is carried by the gas. So I'll give you the very short story here. The main idea is that you can understand that essentially fully from the understanding of instabilities. So I'll just say that it's understood. What understood as what I'm going to write as piggybacking instabilities. Piggybacking instabilities meaning that, well, we can explain most of what's happening here by just thinking about a Kelvin-Helmholtz wave. We've talked about this first tendency of the jet to undergo Kelvin-Helmholtz that feeds into a Rayleigh-Taylor wave that feeds into a Rayleigh-Plateau wave. And there's those absolutely beautiful images. So those are those corresponding images. And I just wanted to mention this. So when you have a high-speed gas flow at the surface, you have shear. And we talked about the fact that this shear will lead to the development of Kelvin-Helmholtz waves. That's this longitudinal wave. The jet will go whoop, whoop, whoop. Once you generate a crest region like this crest region is now being pulled into the gas. Well, if you think about what that means that we have liquid accelerating into a gas. From the perspective, if you were to think about this acceleration being caused by gravity, we're again getting back into a Rayleigh-Taylor type of situation. We have heavy stuff accelerated into light stuff. That wave here that grows and gets accelerated into the gas, that wave should be unstable itself. So primary wave Kelvin-Helmholtz, as it accelerates, it is as if you had a pool of water, water pooling on the ceiling. This thing will want to drip. It will become unstable. So first, KH wave due to shear. Second, you're now pulling on this KH wave. You're accelerating. A wave crest of liquid into a gas. This is subject to Rayleigh-Taylor instabilities. That means that my crest like this will become unstable, and I don't know if I'm showing this anywhere here, right here. That's what I'm showing here. That crest should now undulate like this. So this right here is your Rayleigh-Taylor. Okay, so this right here is your Kelvin-Helmholtz. Then you have your Rayleigh-Taylor. As now you have a wave like this that is combined with a wave like this. That means you have this little bulging region. As this thing gets pulled, now you have a ligament. As you pull on the ligament becomes a little tiny liquid cylinder. This is subject to Rayleigh plateau. So this is now your ligament. And so right here we have our Rayleigh plateau breakup. So this is a beautiful situation because the liquid is laminar. It is literally a collection of very canonical instabilities that lead to the formation of drops. So this is really cool. It can be studied very nicely experimentally. You don't have a whole lot of mess, and that leads to those type of beautiful pictures. Again, with those cool-looking digitations of a wave that follows with a wave that forms fingers, and those fingers that later on just break into a collection of drops. All right, so this I wanted to mention because it's kind of nifty to come up with a very clean, direct use of stability theory to help you explain a very complex flow problem. It's rare to find those opportunities. All right, I'll stop here. I think I checked all the, I think, I'm not 100% sure, but of all the little things I left behind, I think this kind of collects, this concludes this list. So I want to thank you again very much for your patience with me, and especially, it's pretty obvious, especially today, that this was a collection of somewhat disconnected ideas. This exercise has certainly helped me a lot in terms of thinking about how this should be structured. So I've appreciated your willingness to serve as, test subjects for this. So thank you. And also I want to thank you for overall your attention, patience, and interest and feedback and all this.